Okay, so maybe we can slowly start again. I will actually start by reiterating what we arrived at in the last discussion, then before moving on. So in the last lecture this morning, we saw that we from the 2 amplitude written down in this impact parameter space representation, we can deduce a quantity which we call the iconal phase. And the nice feature of this writing is that it resounds contributions that have to do, in particular, as we saw, with a single graviton exchange, which resounds to this delta zero. And in a sense, this takes into account the exchange of many now graviton exchanges, which all have this sort of ladder-like, ladder and cross-ladder form. And then there can be non-exponentiated quantities, let me call them big delta, which are instead small in the classical limit. We will not go too much in detail about those instead. But the nice feature of this iconal is that it is very large to leading order in the classical limit, so it's proportional to this gm squared over h bar. But then order by order in the perturbation theory, it only receives corrections that are sized by the small pm parameter gm over v. In particular, thanks to this relation, and the formula that you have in your notes from previous lecture, we can write down now the formula for the leading order impulse, which is just 4g m1 and 2 sigma squared minus 1/2 divided by b square root of sigma squared minus 1. So just to remind you, this is for a 2-to-2 process in which we have two incoming and outgoing velocities, and this is our angle theta, or if you prefer, this is the momentum transfer. So this is the leading order contribution. The next leading order contribution simply comes from taking the derivative of the next leading order iconal, which we also have. So it's 3 pi g squared m1 m2 m1 plus m2 5 sigma squared minus 1 over b squared, and there's also a factor of 4. That's right. So okay, these are our predictions that we derived from amplitudes in this morning. And well, before moving on, I just wanted to pause briefly to analyze a bit their property in different regimes, which may be instructive. So the first thing I wanted to say, okay, you can convert these to the deflection angle by using this formula, of course, and to leading order for small theta, of course, is just theta, so times p. So we can just multiply and divide by p, and then we can use that identity I wrote down at some point earlier on to make perhaps the writing even a bit more transparent. So the theta 1 pm is just 4g times the energy times this sigma squared minus 1/2 over b, sorry. And then the theta 2 pm instead, well, it's very similar to the other one, but let me write it down. Okay, so what I wanted to do is to study their limit now, since the benefit of this post-Minkowskian approximation is that, as you can see, we have some generic function of the sigma, or if we prefer of the velocity. To remind you that sigma is just 1 divided by the square root of 1 minus the relative velocity as defined in the rest frame of one body or the other, and therefore let's do it. So the first limit I wanted to check is the high energy limit. So this would be a limit in which sigma tends to infinity, right? When the two objects are moving so fast that they become ultra-relativistic. Of course, we immediately face a problem, namely the fact that gravity interacts with the energy. If we try to send the velocity to infinity without doing anything specific, we are just going to be beyond the regime of validity of our PM approximation, right? Because the energy is tending to infinity, gravity couples to the energy, the interaction becomes infinite. So, of course, what we want to do is to take the energy to infinity while keeping the impact parameter also very big in such a way that this parameter G over B is fixed and small. Otherwise, it doesn't really make much sense to trust this leading order and subleading order PM results. Then this this quantity here, as you can see, just behaves as in a smooth way, because the sigma squared just cancel from the numerator and denominator, so this goes like 4GE over B. And as you can see, the dependence on the mass has dropped out, so we are in a regime in which the energy is so big compared to the masses that these two objects just behave like null rays or shock waves, if you prefer, and they are just massless. So this actually agrees with the results, for instance, obtained by Drey-Toft for massless shock waves. And instead here something funny happens. As you can see, we can rewrite theta 2pm as a number times GE over B squared, which would be the natural guess, right? This goes like G over B, this should go like G over B squared, but here we are missing a factor of energy, so we actually find something like M1 plus M2 divided by the energy, right? This means that this quantity actually is tending to zero in this ultra-relativistic limit, and in fact this is a general expected feature of this massless scattering, the fact that studying the amplitude, the corrections, well, you don't have a mass that is just linear in the energy scale. You can only build something that like goes like S, which is square of the energy, and so you can discuss a power counting rule according to which only the odd PM contributions are supposed to be non-vanishing. So this is somehow expected. And the other comment was about this the other limit, so the small velocity. So sigma tends to 1, or yeah, or if you want, v tends to 0, right, the velocity. So in this regime, we are supposed to recover what our post-Newtonian colleagues derive. So let's write it down, what happens. So theta 1 pm in this regime tends to 2 gm. Of course, the total mass of the object behaves like the, it's almost like the energy, right? The difference is something of order velocity squared, divided by b v squared, v being this guy over there. And instead, theta 2 pm goes like 3 pi g squared m squared divided by b squared velocity squared. So now I wanted to spend a word just about how one now compares with Pn, right? Post-Newtonian. So you remember in the post-Newtonian limit, we would be expanding in a regime in which Gm over B and V squared are both small of the same order. So what tells you at which order you are in the post-Newtonian expansion is can be taken into account by realizing that G scales like 1 and V scales like 1/2, right? Because there is a square here. So here you see we have a G in the numerator and a V squared in the denominator, so this doesn't scale, which means that they are at 0 post-Newtonian order, right? So this would be really something that we can deduce from the Newtonian result that we all learn in undergrad. And instead here we have a G squared in the numerator and just a V squared in the denominator, so this is a 1pn. So this is beyond what the Newtonian result gives you. So let's compare with what this result. So if you do the result by solving the two-body problem in the Keplerian limit, on the Keplerian setup, what you find is that theta Newtonian is 2. Okay, then you can write it in several different ways. The one I have here in my notes is the arctan of Gm over Bv squared. And so here I come back to a question I think I was mentioning when answering a question earlier on. The two results are not the same. What is true is that if you now re-expand this for small g, they become the same. But of course, there will be corrections of order g cube, right? Because the arctan has an odd expansion for smaller arguments. So then what we see is that the Newtonian order, we get agreement with the small velocity expansion of the PM result, between the small velocity expansion of the PM result and the small g expansion of the Newtonian result. And then we don't have anything of order g squared, but this is correct because this contribution starts at the next order in the Newtonian counting. So we don't expect to see it at Keplerian, from the Keplerian angle. Okay. So before so this is what we learned by studying the 3-level and 1-loop amplitude. And actually what we have done, although with this sort of fancier language, has been to reproduce calculations that people had done already in the 50s and 70s, just by completely different methods, just by studying the gravitational two-body problem in general relativity, expanding the field equations and the equations for the particle trajectories order by order in this small ratio gm over b, and solving them to leading and next to leading order. So we didn't do very well, right? We use this sort of fancier language to reproduce results that are very, very old. So before moving on, I wanted to actually at least write down the first result that had been obtained by this kind of amplitude method that had not been obtained by standard GR calculations. And this is that the two-loop result. Of course, I will not show, not even attempt to construct the integrand on the blackboard for the two-loop case, but the result is that, of course, you can go on, and there is a two-loop iconal, which has a real and an imaginary part. This is a bit the novelty I wanted to emphasize, and which will serve as a sort of bridge to the next part of the lectures. So let me just write it down. It's a bit long, but I think it's worth showing it at least once in order to, to show that there is some meat under all this. So in principle, the calculation is very it's difficult, of course, but is a bit less difficult apparently than what in the GR setup one would have done. Otherwise, would have been difficult to obtain this before the standard GR approach. And then I want to emphasize that the logic is really the same as the one that we sketched or we discussed more in detail this morning. There is an integrand, you derive it, you neglect things that would not matter for our long range interaction. You perform all the integrals, take the derivative with the Fourier transform to go to impact parameter, match to the iconal. This is the result that you get. I will define these symbols in a second. Calligraphic I is this other function. And then here I'm out of space. That's the real part of the iconal. So basically what we are doing is that we are expanding to next order this phase over here. And also there is a novelty, which is that there is an imaginary part. So let me write it down. Its expression is actually very simple. And then discuss it. There we go. So let me discuss a bit the meaning of the various pieces of this answer that people got in 2019, 2020, 2021, depending on the various pieces. So there are, in the real part, which is the one that enters the stationary phase approximation, and therefore the one that matters to get the angle. So more precisely, this is the right thing to use to calculate the physical part of the deflection. There are two pieces. One is the one in this square bracket here, which was calculated by Zwiebern and collaborators in 2019, and goes under the name of potential or conservative piece. And the reason why this is the case is that when you calculate its contributions to theta 3 p.m. now, so the 3 p.m. deflection angle, it only contributes with contributions that are corrections of order v to the 2n, so even powers of the velocity. Or, according to the Pn counting that we just discussed, integer Pn contributions, right? Because they have v squared to some power, so they are integer in this counting. So intuitively, these are time reversal even contributions that are associated just to the fact that each black hole feels the gravitational pull of the other one, so a conservative sort of potential-like effect. And then there is a different piece, this guy over here, which instead behaves in a different way. These are contributes to theta 3pm by corrections that are odd in the velocity, so they are half odd pn contributions, and this with different efforts, etc., has been identified as a dissipative effect, which comes in particular due to the fact that the field, the particles, the two-body system interacts with the gravitational fields and loses a little bit of energy to angular momentum. In particular, to this order, the contribution is really due to a loss of angular momentum that back reacts on the trajectory, and this is why it's called radiation reaction bit. Now, as you can see, as I try to make apparent in the writing of these two pieces, this radiation reaction part seems to be very much related to, so this is the expression, this is this calligraphic I function written over there. It's very much related to this imaginary part. So my objective in the next few minutes would be to understand why this connection appears. In particular, this function, it appears literally as the same function appearing in front of this 1 over epsilon. So the imaginary part is infrared divergent. It has a 1 over epsilon in dim reg, and it also comes with a log of sigma squared minus 1 in the finite part. We will see in a minute why. And so this seems interesting. The other comment that I wanted to make is that now you can study again this behavior in the high energy and small velocity limit. Let me not do it in detail on the blackboard, just highlight a bit the features. So in the small velocity limit, there is a piece that goes like 0 pn again, so that we could deduce again from this formula, and this comes from this piece over here. Instead, there is a contribution which scales like 2 pn, and it would come from this second line. Finally, and instead, of course, as I said, this radiation reaction piece would be half odd pn. It would start at 2.5 pn. So maybe just to summarize, 2.5. And here, well, okay, there are both 0 pn plus other stuff and 2 pn plus other stuff. Instead, another interesting regime is the ultra-relativistic one, in which one seems to encounter a problem. In particular, if you try to take exactly the same limit we took over there, so sigma goes to infinity for g over b fixed, you would seem to encounter a problem due to this arc Koch. So this arc Koch for large sigma becomes a logarithm of sigma, and would seem to induce a scaling that goes like GE, maybe let me just make a GE over B cube, which is what you expect for the angle, times log of sigma. However, sigma is as big as you want in this regime, even for G over B fixed, so this would mean that the deflection angle is infinite, which is, of course, nonsensical. However, what saves the day is precisely the addition of this radiation reaction contribution, which for small velocity does not talk to this piece in red at all. However, for large velocity, you see it also has an arc Koch, and the two actually cancel out precisely to eliminate this log and leave behind the result obtained by Amati, Cefaloni, and Veneziano in 1990 for the massless case. So exactly like the 1 p.m. situation. Okay, so this is good. However, let me come back to this imaginary part right now. So you remember in the previous lecture, we briefly touched upon the fact that the amplitude can be complicated, but it has to obey some nice constraints which have to do with unitarity. So if you want the generalized optical theorem, told us that twice the imaginary part of the amplitude, particularly our 2 to 2 amplitude we are looking at right now, as to satisfy constraints, so they must be related to cuts of, well, order by order in G, cuts of lower order amplitude. In particular, we used earlier this 2-particle channel, which allowed us to calculate the imaginary part of the 2 to 2 amplitude at order G squared. But now we want to go one order beyond that, so we want to go order G cubed. So in principle, if we want to calculate the full imaginary part of the 2 lobe amplitude, we also need to look at this 3-particle cut, and then there can be others which don't matter at order G cubed. One can discuss this in full generality. However, what happens, and let me sort of try to sell it to you in analogy with what happened at one loop. You can actually show that this is correct, but it would take us a few minutes, so which I want to spend otherwise. What happens is that when you take the Fourier transform of this, so Fourier transform of previous equation, and match to the Eikonal exponentiation over there, it happens that this cut goes away thanks to the expansion of the exponential. This is exactly what happened at one loop, right? We also had there a minus, well, a plus I over 2 times something, which eventually was just delta 0 square. So it did not contribute to the phase sitting there. So exactly the same thing happens. So the two particle channel is already encoded in the exponentiation, is already in the iconal exponentiation. So the upshot of this is that if you are interested in the imaginary part of the exponent that appears there, you don't need this. You only need that guy over there. So the bottom line is that twice the imaginary part of the amplitude would have these two cuts, but twice the imaginary part of the two-loop iconal only has this three-particle cut. Okay, it turns out that this will be enough for us to understand this connection between this radiation reaction part and the imaginary part in the iconal. Oops. So yeah, more precisely, I mean, I'm drawing blobs which may be considered not entirely precise, but okay, if I want to be consistent with my notation for blobs, the blobs are in momentum space, and then you have to take the Fourier transform. So the point I wanted to convey is twofold. On the one hand, we can try to play a similar game to the one that we played earlier today, when we remember we also had the Fourier transform of a cut. Now, earlier this morning, it was just the two particle cut, and what we were able to argue, well, to derive, was that this was just the Fourier transform of a single blob squared, right? Plus higher orders in B, which we did not care about. Now, what we want to do is to play the same game, but now the blob is going to be a bit more complicated. It involves, in particular, a new ingredient, this 5-point amplitude. So let me introduce some notation for that. So this will be a new sort of protagonist of our discussions. Now, instead of being just a function of S and T like the 2-2 amplitude, this 2-3 amplitude has some more structure. It has P1, P2, P3, P4, and let's say K, the emitted graviton. So in particular, there will be more invariants that you can build, right? There is still sigma P1 dot P2 divided by, say, M1 and 2. However, this will be different from the one calculated from P3 and P4 due to the emission of radiation. And so other two invariants that you can build, for instance, P1.k and P2.k, which are new. And moreover, it's natural to define two momentum transfers now, Q1 and Q2, which now by momentum conservation simply add up to minus K. Okay, so this is our new ingredient. And now our objective is to massage this object over here. So maybe I can do it in another blackboard. Any questions? So this is the first order at which we see some effects due to radiation entering, whereas up to order G squared, it was entirely consistent to treat the problem as if it was a conservative process. Although, of course, we know that this is not the case, and this is the reason why we observe them, right? Because they emit gravitational waves. So this is the first sign of that. So let me calculate twice this 3-particle cut. Maybe at least once, let me write it down in sort of full glory. There is an integral over the intermediate phase space of these three particles. Let me choose some routing for the momentum. This is going to be minus P1 plus Q1. And this is P1, right? So it's a function of Q1 and K, where K is the momentum of the graviton, as over there. times A0 Q1 K. So the leading order of the thing over there. And then in principle, I would need to do exactly what I did earlier this morning. So contract with some polarizations. And then let me try to get my conventions right. Q1 minus Q is the momentum that flows in the other amplitude, the one that appears on the other side, and K. And sum over the possible helicities, right? However, here we can use our formula that already appeared this morning. This can be traded for this projector mu nu rho sigma, but as long as this 2 to 3 amplitude satisfies the, say, the word identity or the gauge invariance condition, we can simply replace this guy with the P that already appeared this morning. Let me not write it down again. It is eta mu rho, eta nu sigma plus, etc., etc. So in fact, let me, for the rest of the lectures, whenever two to three amplitudes, so two objects with these two indices appear together, and I'm not writing down the indices, it means they are actually contracted with this structure here. So, say my short notation is just gonna be this one. And this is the tree level, of course. Very good. So what happens here now when you try to take the Fourier transform of this is that once again this sort of convolution Q1 minus K factorizes, but it factorizes in a slightly non-trivial way, in the sense that it is true that it factorizes as the integral over K. So there is a leftover integral over this momentum K, which acts as a spectator with respect to the convolution, as you can see sort of from this equation. So let me denote it like this. This would be an integral over the phase space of the gravity, right? So there the measure is this one. And there are indeed some A tilde of BK A tilde star that enter. So again, they are contracted with this P mu nu rho sigma, which also is also a spectator because it no longer depends on any variable, just a combination of etas with different indices. And the novelty is that this A tilde is not the usual Fourier transform that we had earlier, which was defined for a process, for a 2-to-2 process, in which you have some incoming, some two-body incoming state and a two-body outgoing state. It's sort of it's a new Fourier transform. Let me again denote it tilde, but I mean, the difference will be apparent because it's applied to an object which is not 2-to-2, it's 2-to-3 now. And the formula is the following. So it's a sort of symmetric generalization dd q1 dd q2. So it's essentially a Fourier transform with respect to both momentum transfers, but now constrained by the fact that they have to satisfy momentum conservation, of course. And they have to obey, I mean, the Fourier transform must still respect the mass shell conditions of particles P3 and P4, so their mass shell delta functions P1 dot Q1, and then in principle there would be, so P4 here is Q1 minus P1, right? So its mass shell condition would be that P1 dot Q1 minus Q1 squared is 0, but since we are to leading order in the classical limit, Q1 are small, etc., I'm going to neglect the Q1 squared here, and similarly for the other one, times the amplitude, which is a function of Q1, Q2, and K, but of course it's only defined on the mass shell condition, e to the I x1 dot Q1 plus x2 dot Q2. And I guess here I have to, well, there is an x1 and an x2. Now what I mean by just A of B instead of A x1, 2 is that B is going to be x1 minus x2. In fact, these, if you redefine x1 equal to B minus x2, you see that you can pull out a phase proportional to e to the minus I x2, for instance, dot k, and a phase which is independent of k, sorry, which is independent of q and therefore of b, would cancel out in this product, right? Because it comes with a plus I here and a minus I here. So from here, you cannot actually deduce this phase, but this choice is the obvious one that makes the result symmetric. So, so we sort of did what we were expecting. The Fourier transform has diagonalized the convolution, but well, how do we actually use this equation? The problem is that this A tilde, to calculate it, to perform it explicitly, is not actually very easy. In fact, as you notice, I didn't write down the result for the 3-level amplitude. The result for the 3-level amplitude, of course, is still a nice rational function. It doesn't pose any particular challenge to write it down. It's just a bit long. But the problem is that performing this Fourier transform is actually a bit challenging. And even at 3-level, you know, whereas for the 2-to-2 case, they were simple. I wrote down the formula, one of the first few formula we discussed this morning. Already here, this A tilde is a bit of a complicated object. So A tilde of bk involves some Bessel function, involves k01 of combinations like this p1.k over m1 v, I guess, say omega, and also some integrals, leftover integrals of this Bessel function. So let me not write it down. And however, this object is very interesting because, as we will see hopefully in the rest of this lecture, or maybe at the beginning of the next one, is that this is actually the gravitational waveform. So the leading order gravitational waveform in frequency domain. But as I said, we will come back to this. For the moment, it's just something appearing in this three-particle cut, which we would like to be able to manipulate in order to understand the structure of that imaginary part, which we can calculate using this cut. So for the rest of today, what I want to do is to use a simplification, which is the fact that if we only are interested in that 1 over epsilon, so that 1 over epsilon is actually as predicted by the structure of infrared divergences that you find in the paper by Weinberg in 65. So in order to deduce it, we can actually restrict this integration to the soft region. So we can apply the soft theorem. And this is what I want to do next. So the objective is still to derive that relation over there. And to do that, let me use the fact that restricting to the soft region, to the soft portion of the K integral, let's say, we can use the soft theorem. The leading order soft theorem, which simply telling us that A0 of Qk, this thing over there, in the small frequency limit, omega goes to 0, or K is proportional to omega, is just square root of 8 pi g, the sum over A that goes from 1 to 4, so the four massive lines, which are hard lines in this case, Pa mu divided by Pa dot k times the 2-to-2 amplitude, which we discussed this morning, which does not depend on k at all, right? So this is the game. Yeah, so for the moment, it's just my choice. I'm just starting to look at this integral from the soft part. The argument, and we will see how this comes about in a second, is that that's where this infrared divergence, the 1 over epsilon, comes from. So this will be enough to calculate the IR divergence. So what you can do now is that you can plug this in, the Fourier transform, which I gave here. What happens as k goes to 0 is that this sort of uglier Fourier transform goes back to the old one, right? Because if k is 0, q1 is just equal to minus q2, and we get back the expression that we used this morning to do the Fourier transform of the 2-to-2 amplitude. So what I'm trying to get at is that what we should do is that we should expand the Weinberg soft factor for small q, right? This is the regime in which we are interested in, this small q versus, or large b if you prefer, approximation. And then what one would find is that this is linear to, is linear in q. There is some operator like this, well, some matrix. I did not write it down explicitly. And then what we have to do, all we have left to do in order to perform that Fourier transform is just to take the Fourier transform of, this is a constant matrix, of q alpha times a0. But this Fourier transform is very simple, because any Fourier transform of this kind, we can just reinterpret q alpha as being a derivative with respect to b, right? As usual in the Fourier transform, products between derivatives, etc. So this is just minus I, the derivative with respect to b of the Fourier transform of a0. But we saw this morning that the Fourier transform of the three-level amplitude is just delta 0, and that the derivative of delta 0 is the leading order impulse in the PM sense. So this is just minus I q1 PM. Is it clear? So here I'm using the fact that f tilde, ft of a0, so a tilde 0 is just delta 0, 2 delta 0, and its derivative is the 1 PM impulse. So as you see, what happens is that effectively the small q appearing in this quantum amplitude after the Fourier transform simply becomes the big Q except for a factor of minus I. So what happens is that effectively I can promote this formula to be valid for generic. What I can do is that I can simply remove this A0, keep this guy, and interpret small q as big Q. It's just that the formula becomes a bit more compact, and then re-expand it at the later stage in small q. The two operations, of course, commute. So what I'm saying is that A0 tilde bk in the soft limit is just square root of 8 pi g sum over A1 4 pa mu pa dot k, which looks like the same, right? Times minus I, in which I replace now P4 is equal to minus P1 plus capital Q1 PM, and P3 is equal to minus P2 minus Q1 PM. Right, this is just a trick. Of course, you could just expand to leading order in Q and keep this O, it's just that I don't want to write it down. And also, as we will see in a second, this mechanism generalizes to higher orders in Q, so this is actually more suggestive. But for the moment, it's just a simplifying trick. So where I'm supposed to erase, maybe this one. So now, as you can see, the expression has become really simple. It's just the Weinberg factor, literally, and we just have to square it and integrate it in order to calculate the IR divergent contribution, or the contribution from the soft region, from the soft portion of the integral to that Fourier transform over there. So let's do it. In the product, and there is a contraction with that P, you remember? So I have to substitute this expression into that box over there, and I get 8 pi g sum over A and B. Yeah, so much for our walk later on. Let's hope for the best. I will keep this lecture longer so we can stop raining in the meantime. No, I'm joking. And then it's convenient to pull out factors of the mass that would come from the contraction between these PAs in one sum and PAs in the other sum, and introduce some notation for their product, which is kind of obvious, but we'll define it in a second. And what else? And then, of course, there are the denominators, which are the actually interesting part, over which we still have to integrate. So what we are doing here, we are restricting to the IR divergent contributions. As I said, we are cutting off the integration over there up to some frequency. Let me call it omega star. And then we have two copies of this denominator. Okay, so these sigma AB are just some shorthand notations for PA dot PB divided by MA and B let's say, absolute value, in the sense that some of them could be positive, some of them could be negative, they are all positive here. Okay, so then we have simplified our life quite a lot. I don't know if you realize, but this would have been a two-loop calculation, which I would have never been able to perform in any kind of detail in front of you at the blackboard. Instead, by restricting to the IR divergent contributions, we were able to use the soft theorem, and the form of the soft theorem is very simple, and it just reduces our calculation to this sort of, well, effectively one loop integral in a sense, right? There is just one variable to integrate over. There is actually a further simplification. In fact, let me try to discuss that integral in some more detail and see where this infrared divergent comes from, which is actually the very reason why we did all of this. So it's a good idea to split the integration over k into angles and frequency. So let me do that. There are some factors of pi that just come from the measure, and then there is an integral up to this omega star of d omega divided by omega. So let's see, here there are 2 powers of omega from the denominator, and then there is a measure d for k, right, divided by k squared effectively, because it's so this is of course scaleless up to the fact that we are in dim reg. So the measure is 4 minus the epsilon dimensional. This is what saves the day. And then we have the integral over the angles of this of these things in which I stripped off the frequency. Let me introduce some notation to denote the sign, whether the particle is outgoing or incoming. So this would be plus for outgoing and minus for incoming, this sign here. So then it becomes EA minus KA dot K hat and EB minus KB. So K are the spatial parts dot K hat times eta A, eta B, I think. Yeah. And then there are 2 pieces. So you see the integral is factorized. There is an integral over the angles. Let me discuss that in a second. But first, let me look at the integral over the frequency. So you see this evaluates to minus omega. Sorry, here there should be a plus because the measure is d minus 4 dimensional. 4 minus 2 epsilon dimensional. So the minus appears in the numerator. Evaluated from 0 and omega star, which is, okay, in dim reg, we choose it precisely in such a way that when we evaluate this at 0, epsilon has a slightly negative imaginary part, so that this gives 0, right? So this is exactly minus, say, omega star to the 2 epsilon divided by 2 epsilon. And then we can expand this for small epsilon, so minus 1 over 2 epsilon plus log of omega star. Now, of course, what this argument is not telling us is what omega star is. It turns out it is actually not really important. It's only important the fact that by dimensional analysis, actually, of course, it would be more precisely something times omega star b. It must be dimensionless. And you remember the first lecture I just said the typical frequencies are of order omega b divided by the velocity. So this thing must be of order the velocity. And then, of course, there could be some complicated dependence on other numbers, like could be square root of 3 times the velocity, etc. But it doesn't matter because the important thing is that is the coefficient of this log. Then there could be something else, but the log of the velocity times something else is the log of the velocity plus something else which we don't care about, right? Which would plus the log of something which we don't care about. So this is irrelevant. And if I didn't make mistakes, I should have derived exactly. There is exactly the same coefficient. If you take out this square root, there is exactly the right coefficient with the minus 1 over epsilon and the log of square root of sigma square minus 1. So already this calculation is telling us that the infrared divergence must come with a friend in the finite part, which must be the log of the velocity, precisely with the same factor. And then let's come to the integral with respect to the angles, which I will not perform for you on the blackboard, but it turns out it's actually also very easy. In fact, you can use, you can either evaluate it by brute force, or you can use a trick. You can realize that since this calculation, since the original integral was scaleless, except for this 1 over epsilon that was saving everything, it's actually independent of the cutoff and therefore Lorentz invariant. And therefore, you can actually evaluate it in a frame which you like. In particular, you can choose to evaluate it in the rest frame of one of the two particles, in which one of these two denominators becomes very, very simple. In particular, it's independent of the angles. So exercise, if you want, which you can choose to solve either by brute force or by using the hint of evaluating in the rest frame, you can show that this integral is KB, sorry, is just 1 over m1 and 2 m a and b, the arc cosh, so the hyperbolic arc cosine of sigma ab divided by square root sigma ab squared. Okay. So now with these two ingredients, you are, I mean, if you want to put back together the pieces, you get a result, which is the following for the imaginary part of 2 delta 2. We have a g over p minus 1 over epsilon plus log of sigma squared minus 1. And then these, the sum over all these functions. Then I will tell you in a moment why I'm bothering writing it down explicitly instead of just letting you do it later. Okay. So there are two reasons. So first, you remember our objective was not actually to calculate this in full glory, but we should actually re-expand it for small q, right? Now for small big q, q1 pm, and in that regime the result is, so maybe, and then the result is very simple. It's 4 pi minus 1 over epsilon. So you can expand this sum over here, and you will realize that it's of order q squared now, and this is reasonable because you remember each of the two Weinberg factor was actually of order q on its own. So of course the sort of square that we are taking must be proportional to the square of q times this calligraphic I, which was already in the right direction, right? The calligraphic I was the function to which the real part of 2 delta 2 RR is proportional. And then we are also in a place to understand the connection why the real part and the imaginary part, right? Which was our objective to begin with. And the reason is unitarity, sorry, analyticity. So, well, actually we are using all the properties in a sense. So there is unitarity because the fact that the imaginary part of delta 2 is fixed in terms of this cut was due to unitarity. And then we are using the soft theorem to come up with a prediction for the infrared divergence. Then from the infrared divergence, we deduce that there should be this log. And the last property is analyticity. So the log must actually come in the complex plane from the boundary value of an analytic function, which is this one. It must have a branch cut for negative, for sigma going in the physical channel. And this is just log of sigma squared minus 1 minus I pi. So the upshot is if there appears a log in the imaginary part, it must actually come with another partner, another friend in the real part, which is exactly the same but multiplied by pi. And this is exactly that pi over there. So at least one calculation we managed to do at 2 loops on the blackboard, and it was thanks to the soft theorem. So this is one thing. So we deduce let's say, we deduce what is actually relevant for im of 2 delta 2. And the other thing I wanted to mention before moving on is the fact that a very similar calculation would allow us, instead of calculating this imaginary part of the icon, it would allow us to calculate another observable, sorry, unobservable. The imaginary part of delta 2 is not an observable, of course, which is the differential energy spectrum in the zero frequency limit. So as omega tends to 0. So let me try to explain why. So the reason is, okay, if you trust this thing that I said at some point, that this Fourier transform of the 5-point amplitude is the waveform. The reason is that there is a formula that well, you all know much better than I, which is the fact that there is an energy flux formula for the two-body system, which is the Bondi mass loss, which tells you that the energy flux is just the integral of the derivative of the waveform, essentially, of the shear as a function of time squared. Okay, if you translate that to frequency domain, this is telling you that the right thing to calculate is the integral of this W squared, the waveform, which for us is just A tilde, essentially, times the frequency. It's exactly the same integral. And then if you want to calculate the differential energy spectrum, which, you know, in general will be a complicated function of the frequency, and this integral tells you the full integral over the whole history of the binary, so over all the frequency in frequency domain. But what you can do is, again, to cut it off, exactly as we cut off our integral over there, up to some small frequency, omega star, and take its derivative with respect to omega star. So this is the calculation that will give you the zero frequency limit of the spectrum, so the value here. And then you can go back, look at the rest of the blackboard, and check what would happen if we were to insert a power of omega from the beginning, right? This is the calculation that we did, and this, sorry, without this derivative, and this is the calculation that we are instructed to do. So we have to multiply by omega and take a derivative with respect to omega star. So maybe let me try to do that. Yeah. Right. So here, sorry, I realize maybe I'm going a bit fast and so superposing two things. So one up to here, as Yannick said, our objective was to calculate as much as possible on the blackboard, but not all, the two-loop iconal. So really the contribution to this phase in the 2-to-2 amplitude at two loops. And then I said, yes, there is a real part. For that you have to do hard calculation. But there is a bit of the real part which comes with a friend in the imaginary part. And then that is the piece that we discussed and we calculated using this unitarity, analyticity, etc., etc. But the objective was still always to calculate the thing in imaginary, in the real part, that real part over there, real part radiation reaction. So if you want, this is a shortcut to calculate the radiation reaction in the real part from the imaginary part, and it's the real part that enters the angle. So when you take the derivative, you have to take the derivative of the real part to get the physical observable, and that is infrared finite. You see, this is the imaginary part, but the real part doesn't have the 1 over epsilon. It's factored out in front, right? So in the end, everything is finite. The prediction for the deflection angle is finite. It's just a property of the amplitude, which I actually want to come back to as to why it is like that. We are going to try to do better, in fact. And now here I was switching to something a bit different. Suppose you were interested, instead of the deflection angle, suppose you were interested in this other observable, which is completely different, right? It's a property of the energy emission spectrum that you observe at your interferometer. You have this complicated curve, but you want to focus on the zero frequency limit. Then this would be the calculation I try to argue. I can justify it better, but maybe for today's purposes, let me try to be sort of practical and just show you how it would go. Then you have to start again and multiply by omega and take a derivative with respect to omega star. So this would simply localize the integral at some omega star and remove, so maybe like this, and remove the divergence, right? Because now this goes like this, and in fact there is no leftover integral, so there is simply nothing here. And so the only difference, okay, you can try to work out the rest, the corrections from here, but the bottom line is that you simply don't have a factor of 4 epsilon. So it's exactly the same. So this formula is still correct. I just have to multiply it by minus 4 epsilon in order to get this zero frequency limit. So yeah, let me cheat a little bit and erase it here. I guess this is it. So here there is a lot of space, but there is nothing. Just 4g over pi times this combination. And then we see what we gained by using the the soft limit. I mean, here I introduce everything just by expanding for small q and then resumming, but you can play this order not just a leading order, you can just go on. At all loop orders, you can formally expand this factor, and then order by order in perturbation theory, all these Fourier transform is going to do is to turn the small q's into the big q's, which are the classical observables. So it turns out that what we got is actually a non-perturbative prediction for the zero frequency limit of the energy emission spectrum. So that's why I sort of cheated a little bit. Instead of expanding, I left it non-expanded, but it turns out that this formula is actually correct to all orders. We will come back as to why this is the case maybe later, but this is sort of nice because I already had on the blackboard, so I thought I would just advertise it a bit in advance. Yeah. So the classical limit is still the fact that the gm squared over h bar is big. That is now the way in which this shows up in the calculation is that we have to exponentiate the exchanges. Now, what I'm arguing here, yes, you're right in a sense. So what I was doing here was perturbative, right? Because I was working at a fixed order g cube, and then performing this derivative order by keeping this a0 non-exponentiated. What I'm saying, and maybe I will try to be more precise later on, is that if you instead use the exponentiated amplitude, so e to the 2I delta 0, indeed, these small q's will become big q's at all orders. And that's precisely, yeah, because of this resummation due to the classical limit. Yeah. In a sense, we turn this small q, which was a quantum exchange, right, of order h bar over b into something that is classically sizable. It doesn't have an h bar. Yeah. Okay, so. Yes, so it has a g cube in front. Unfortunately, I think, well, yeah, you see a bit over there, it's order g cube, exactly. Very good. So now, unless there are further questions, my idea would be to try to be a bit more systematic about the inclusion of this 2 to 3 amplitude. So up to now, the logic has been, let's try to milk as much information as possible from the 2 to 2 amplitude. But in a sense, coming back to the point that was raised earlier, in a sense, the fact that this imaginary part shows up in the iconal, and in fact this infrared divergence is telling us something very physical that we have to address more seriously, namely the fact that considering a strictly 2 to 2, so strictly elastic two-body process is actually inconsistent. And the reason is that, I mean, look over there, if you set epsilon equal to 0, it means that the probability amplitude, so the probability amplitude of our process, e to the 2I delta, is e to the 2I, the real part of delta, minus the imaginary part of 2 delta, but the imaginary part is plus infinity, and therefore this probability amplitude is 0. We are trying to look at the probability amplitude for a 2 to 2 process to happen without any radiation, and we find that the probability is 0. So at some point we have to start including radiation in order to make it non-zero. And this is exactly what I wanted to do now. So, so precisely in order to avoid having this infrared divergent imaginary part, the right thing to do is to come up with a better approximation for the S matrix. Essentially, up to now, we were trying to pretend that the S matrix only connects two body states to another two-body state, but this is not the case. It means that it must connect a two-body state to a two-body state which on top has some radiation. And the idea is to promote the iconal phase to an iconal operator. So up to now, we were essentially approximating the S matrix just by a phase, roughly, right? Now what we want to do is to promote this to an operator in which there is a phase, e to the real part of 2 delta, and then there is an operator part, which involves this 2 to 3 amplitude in a specific way. So for the moment, maybe let me be slightly less ambitious. Instead of trying to include the full 2 to 3 amplitude, let me just include its soft limit, which you have under better control thanks to Weinberg, essentially. So okay, the soft iconal operator. And if time permits, maybe tomorrow I will try to see how we go beyond the soft approximation. So the idea is to include this guy plus an operator part, which is essentially this W. Let me try to get my conventions right. Yeah. Exactly. Yeah, exactly. So indeed. So the 2-to-2 process is not allowed just because it the probability amplitude is 0, it tends to 0 as d tends to 4. Still, we can use the real part of the phase to deduce the classical observable at this order. Of course, it strongly suggests that you need to do something better if you want to go on, because this, in a sense, here we were a bit lucky. So this is somehow the way to go. Another way of performing the connection, which I kind of hinted at some point, I was kind of planning to mention it again, but not sure if I really have time. Maybe let me take 5 minutes now to go back to a slightly different perspective. So here, as I said, we are trying to focus on this exponentiated picture. Another picture is to say, okay, forget about the exponentiation. Let's see how we can directly connect the perturbative amplitude to the perturbative observable without going through an exponentiation. So that would be somehow the idea proposed by Kosover, maybe O'Connell in 1918. So the idea there is to prepare some initial state, which is the tensor product of two well-separated particle states, in which one of the two is each of the two is given by a wave packet. Let me, sorry, scroll a bit back in my notes. There we go. So of course there is an integral over the phase space of, say, particle 1, etc., etc. The important bit is that there is this exponential, b1 p1 times p1, maybe minus p1 in my convention, times some wave packet. And now the idea is that this is your in state, if you want, let me call it really in. And then you can calculate observables. For instance, if you're interested in the deflection of particle 1 or in the spectrum, you just need to insert some operator in the state out. Let me call it O, any operator, which is given by acting with the S matrix. Now, here I'm not going to go into detail because I wanted to present a slightly different selection of material, but what turns out is the fact that this formula, if you write down the observable properly, in particular here, you can think of this as being, for instance, for the energy, it's just going to be the integral over, so here the operator that you insert would be just K, A dagger A, right? Inserted in this guy and properly cut off in order to get the spectrum instead of the total integrated energy. And then what you can see is that you can just relate each of the insertions of this A and A dagger to a matrix, or to a T matrix element, to an amplitude, and therefore get an expression of the expectation value of the operator in terms of amplitudes. It turns out that this is exactly equivalent to what we are doing, although in a slightly non-trivial way that, well, I don't have really time to explain right now. But just to mention, in this representation here, for the impulse, you would see explicitly that this imaginary part simply goes away, also perturbatively at G cube order, which is exactly what was happening for us just by looking at the real part, right? Okay, so let me try to go back to this inelastic iconal operator. So here, the idea is that for today, we will approximate these W's instead of just, so tomorrow we will try to see what happens if here we put the full 2 to 3 amplitude in its full glory. Here instead, today we're going to approximate these guys just by their Weinberg limit. So say that W mu is literally our, W tilde is literally square root of 8 pi g, sum over PA mu. Where now, importantly, this mechanism that I was mentioning here applies. So So now, indeed, since we have exponentiated and we went from impact parameter to momentum space, we have turned all the small q's into big q's, right? So now, literally, P1 is equal to minus P4 plus capital Q, and P3 is equal to P3 plus P4, sorry, P3 plus P2 equal to minus Q, where Q is capital Q. And the reason for that is that you can think of, well, I'm not repeating this material because I'm sure in front of this audience would be a bit redundant. We all know the derivation of the Weinberg theorem. We know that it relies on the fact that soft emissions are uncorrelated, right? To leading order, they just exponentiate simultaneously, multiple soft emissions, and this translates in the fact that you can write them down as a coherent state, in a coherent state approximation. For soft graviton emission. So what would happen if you were to dress your 222 amplitude by many soft emissions is that you would just have a product multiplied by the right combinatoric factor of many of these soft factors, and then you can just sum over all of them, and they also exponentiate. And since both the exchanges and the emissions exponentiate, at least in this soft regime, it's very natural to write down this operator. In order to make it a bit more quantitative, since I'm not really giving any proof of that, let me at least make a check. Let me check that when we go back from this to this, we get something consistent. So maybe I can try to do that in this blackboard over here. And then we will use it. So the idea here is to come up with a better approximation for our S matrix in the classical limit, and then once we convinced ourselves that it makes sense, to use it to calculate some different observables. So let's say check or sanity check. Suppose we now project this operator back in a state that has no gravitons. So 0, 0. What would happen in order to let the annihilation operators act on the ket and the creation operators act on the bra? In order to get rid of them, we have to separate out this exponential over here, right? And this we can do by means of the Baker-Campbell-Hausdorff formula. So then we go at e to the 2i real part of delta, e to the, you would get 1/2. And then from the integral of the commutator, since the commutator effectively localizes one of the two integrals that you have, you get precisely the integral of the w squared. So w star. And I think there should be probably also a minus sign here. Of course, now we cut off everything up to our omega star, precisely because we are staying in this soft frequency approximation. Tomorrow, we will see what happens when we try to go beyond this. But now, if you compare with the calculation that we did just a few minutes ago, the one with, okay, where some steps of that are still over there, this is precisely the calculation that gave us the imaginary part of delta 2, right? So. Does it make sense? So you see that the fact that this imaginary part was appearing was precisely due to the fact that we were sticking to states that didn't have any graviton, so we're just the vacuum for these A and A Dagger operators, whereas now this new say, proposal makes more sense, and this is why it doesn't have the infrared divergence imaginary part here. This comes back when you project onto a state that doesn't have any gravitons. Okay, this is just a sanity check, of course. Checking this formula requires you to, again, to perform the calculation that we did earlier. So, well, in the small frequency limit, you can be happy about this derivation that Weinberg gave. So we know that they also exponentiate. Tomorrow we will discuss if they also exponentiate beyond the soft limit. So before using it, actually let me make another remark or state another caveat. So the first quantity that we want to use this operator for could be really the gravitational waveform, to justify why this is the gravitational waveform itself, as I mentioned a few minutes ago. However, there is one subtlety, the fact that this exponentiation of infrared soft emissions was discussed by Weinberg, really having in mind soft gravitons, which are gravitons with very long wavelength or very small frequency, but non-zero. So what Weinberg didn't really tell us, what we have to figure out today before we go on, is how to actually approach the limit k goes to 0. And the reason is that some of the quantities that we will discuss are actually sensitive to this zero frequency, let's say, value in the spectrum, this lower bound in the spectrum. So if you go back and you think again about the derivation of the soft theorem, you remember there is this argument. It's very simple but very powerful. You have some line, some soft emission from the line, and this dominates the contribution in which the line is attached to the external line, because it leaves behind a propagator which would scale. Now let me neglect the factors, but since k squared is equal to 0 and p squared is equal to m squared, this essentially goes like p dot k, right? And this is the reason why we have p dot k in the soft factor. One way of trying to reconstruct how we should include a prescription to go near epsilon equal to 0 comes from the I epsilon prescription that the propagator has, which tells us that we should promote this to be p dot k minus I epsilon in case we ever need to go near k equal to 0. So this is what we're going to do. It turns out for some observables it's irrelevant, and for some others it's important. In particular, as we will see in a second, in order to include this sort of Coulombic field of the binary, it is important, and also for the angular momentum. So what happens if you choose to include or not to include this I epsilon? So if you want, here what I'm writing down is in a sense a principal value prescription to go near k equal to 0. If you include the I epsilon, two things change. Yeah, just maybe let me write them down and then come back to your point. So there are two possible choices, what I'm calling FW, and there is another one that I'm calling, I guess, F, which you replace this with P dot K minus I epsilon. So this is one thing that changes. And the other thing that changes is that it's a bit more subtle to write it down in this way as an exponential of an operator. What happens is that you don't get real part of 2 delta. You actually get real part of 2 delta minus the radiation reaction part. So 2 delta tilde, so no radiation reaction part here. So, you know, earlier on I had this real part of delta 2, which had a conservative piece and a radiation reaction piece, and we discussed the two different properties. It turns out that this doesn't have the radiation reaction part, and that's correct, because if you then try to calculate the impulse again using this other Eikenol operator, you get it again from this minus I epsilon. But this is a subtlety that you don't need to care about right now. Yeah. Yeah. So I would say that up to here, it just relies on the Eikenol exponentiation, which at least up to delta 1, delta 2 is being shown. Sorry, delta 0, delta 1 is being shown. For delta 2 is a bit of a guess. So there is some, actually it's being shown that just for the 2 to 2 case, it doesn't really exponentiate. That's why we want to go to this other framework. The exponentiation of the soft graviton emission, I would say that it's a proof that is in Weinberg in a sense, because they are uncorrelated. This is, well, I think in the paper in 65, when then he uses this to discuss the infrared divergences. So he really checks that, you know, including, well, the only non-trivial case that you have to check is when you include two of them on the same line, right? You have to check that if including k and k prime is the same as including k prime and k, and this is actually the case for the strict soft limit. This is more subtle beyond the soft limit. So I would say that in the soft limit, this is really, I mean, yeah, I would call it a proof. And instead, tomorrow we discuss a more conjectural version of this, which has to do with promoting this formula beyond the soft limit, but to the first few leading order in this classical limit, which we are discussing in the lecture. So I would say that's more conjectural, although it's expected to work, and up to now it's been working at the first few orders that people have checked. Yeah. Yeah. No, we're not modifying QFT. We are just we're just enlarging the set of amplitudes we are looking at. This morning, we were trying to find an exponential structure just in the 2 to 2 amplitude. And then, by calculating this imaginary part, we realized that's probably not a good idea to just use the 2 to 2 amplitude. Then what we are trying to do now is to use still an exponential form. I mean, an exponential approximation for the S matrix. It's just not just, now it's not just the 2 to 2 amplitude, it's the 2 to 2 amplitude and the 2 to 3 amplitude combined in this way. And then, okay, now we are going to use it to actually calculate some different observable. This is, after all, the goal. This morning, we were only able to calculate the deflection angle. Now we are going to be able to also calculate things that have to do with the gravitational field. Yeah, in a sense, this is supposed to be the classical approximation for the S matrix. And then we are going to use it to calculate classical observables. Yeah, that's what I'm going to do next. So it's not that we are modifying quantum field theory. We are trying to come up with a good enough approximation of our QFT S matrix, a semi-classical approximation that we then can use to calculate classical observables. It's a bit the other way around. We are modifying our ansatz to simplify the S matrix rather than trying to modify the theory. The theory stays the same. It's just our way of calculating it that changes a little bit. And by the way, let me also emphasize that if one doesn't like the icon exponentiation, I'm not forcing anybody to use it. One can still also use the good old KMOC, which is a bit more, perhaps a bit more systematic in the sense that one doesn't really rely on any exponentiated structure. One can really work order by order in perturbation theory and then check the agreement with the formula that we derive here. Okay, so the first application I had in mind, which, I mean, this application will be a bit schematic because I'm running out of time a little bit, is going to be the gravitational waveform. So the idea is going to be very much the same as here. We're going to use some quantum operator, insert it, and then approximate the final state as the S matrix acting on the in state. It's just that instead of using the full S matrix, we are going to use our iconal, simplified iconal S matrix. So let me start by discussing the gravitational waveform. So, so yeah, maybe, yeah, let me write down. So the in state is still going to be this approximation, this superposition of two particle states. In this case, we are actually going to consider them as background, whose dynamic we already resolved by calculating this 2 delta here. So we are all, I mean, I'm going to denote this as 0 in the sense that it doesn't contain any of these soft graviton. And then the out state is going to be, it's just that today we are doing this soft approximation, since in the soft limit these things don't actually modify the dynamics of the hard process. We can just neglect the labels associated to the massive object or the hard object. And then this is going to be S in, where for S we are going to use this, maybe let me call it Si to emphasize that this is as an approximation, as we were discussing a minute ago. Okay, and then we can use, in principle, operators and take the expectation value. And this is going to be our prediction for what a classical observable is. In particular, if we want to look at the gravitational waveform, we better look at the gravitational field. Which I'm later on going to contract with transverse traceless polarization, so don't worry for a few minutes I will use free indices, but the result will just involve the transverse traceless part. Okay, so what we're going to do is we are going to insert this operator in this sandwich, and for S, we're going to use this thing over here. And now two slightly different things might happen, depending on whether you want to use this version of the icon operator or this version. Let me use this one, because I like it a bit better. It doesn't really matter for the moment. Let me stick with this one. So, I mean, we all know how to manipulate expressions with creation and annihilation operators. What happens is that A, sorry, A is going to pull down from this sandwich of exponentials, we're going to pull down the coefficient of a dagger and vice versa, right? So so this is pulling down the coefficient of the guy over there, e to the I k dot x, and then minus I0, plus the complex conjugate, right? So okay. So this is in principle an expression that is valid for generic x, but of course we know that we can only rely on it very far away from the scattering, right? After all, we want to stay in this regime of weak gravitational interactions, so we want to take the familiar limit for this x approaching future null infinity, or if you prefer, introducing retarded coordinates for fixed u, the retarded time. So let me say that x mu is u t mu plus r and mu, where t mu in our reference frame, in the reference frames of the frame of the detector, will be this thing, and n will be 1, n. And then we want to discuss the limit of this quantity as x goes to as r goes to infinity for fixed u and n. This is, I'm sure, a familiar step for many people here who have, are familiar with the connections between soft theorems and memory effects and the BMS symmetry. So maybe let me a bit quick on this. So the bottom line is this h mu nu of x, which differs by this expectation value just by a normalization. Let me remind you that there is a difference between the canonically normalized and then the dimensionless gravitational fluctuation, which is 2 kappa h mu nu. This is the canonically normalized field, which was the one we were using there, and this would be the metric fluctuation, really g mu nu minus eta mu nu, so dimensionless. The dimensionless metric fluctuation. So this h mu nu, as r goes to infinity and fixed u and x goes like 4g over r. The integral from, well, in principle there will be two integrals, one from 0 to infinity, which comes from this guy, and another from, let's say, minus infinity to infinity from this guy, but you can check that they actually recombine into an integral from minus infinity to infinity, in this case, of our Weinberg factor. And I think I'm missing a sum over here. And then I have to tell you what k is, and k has become equal to omega, the integrated frequency here, times the direction of observation n, which is appearing here, right? So as I'm sure many of you are familiar with, in this limit, this integral over k becomes localized in the direction which you are taking the null, the limit to scribe plus, right? Okay, so what we are left to do, and by the way, at some point, there was a cutoff omega star that I introduced in order to stay in the soft approximation limit for this iconal operator, and instead here I've dropped it. I am no longer including an omega star cutoff here, but of course, as by now it's become increasingly familiar during these lectures, the meaning is that since we are only interested in the limit of the integral for small omega, the result is only going to be reliable for large, oops, I forgot the exponential factor. Is only going to be reliable for large values of retarded time. So if you want, this is a good approximation of the time domain waveform for large absolute values of the retarded time. So valid for large U. And then the reason why it was kind of important to carry around this I0 or I epsilon is the fact that we now can use that to perform the integral with respect to the frequency without too much subtleties. We only have to remember the representation, the integral representation of the theta function. Omega, well, let me call it A. This is theta of A, right? And this is, I mean, you can go more in detail into these steps. I wanted to be a bit quicker in order to actually discuss the result before concluding the lecture. So as you can see here, you will have a sum over incoming and outgoing states. You remember our convention was that these PA are future directed for the outgoing particles and past directed for the incoming particle. This means that you will have a different sign here depending on whether the particle is incoming or outgoing. And this means that if you go through the exercise, you will find that some of them have a theta of plus u. This is for the outgoing particles, and some of them instead of a theta of minus u. This is for the incoming particles. So the final result that we are going to end with, I guess, for today, since it's a bit late, is this approximation for the waveform. Now let me include the TT projector, as I promised I would do. Sum over all the particles, PA rho, PA sigma, theta of eta A u. So again, this would be plus for outgoing and minus for incoming. So it's a funny way of writing sum over in states times theta of minus u plus sum over the out states theta of plus u. PA, so min minus theta A, PA dot n. Okay. So let me draw a picture and then conclude. Maybe let me draw it over there. So from this derivation, from the iconal operator, we recovered a very nice result that in particular was discussed in a paper by Strominger and Zhiboidov, namely the fact that the Fourier transform of the leading orders of theorem is the memory effect, right? This is exactly the formula for the memory effect. If the picture I wanted to draw is so there is a value that we can predict in the far future. So for theta of u, the argument of the theta u positive, which means positive u, but remember we can only trust this for large u, so there is an intermediate region to which we don't have access. This would be related to our waveform beyond the soft limit, which we will discuss maybe tomorrow. So here we have this sum over the outgoing, and here a sum over the incoming particles of this p dot n, and the difference between two is the memory effect. Maybe a bit schematic, some of out man, some of in. Now, the reason why I was sort of careful about this I epsilon doesn't really have to do with the memory. One can check that changing the epsilon prescription, of course, could only add a constant value to this field. So what happens is that it could only shift this up and down. It wouldn't change the difference between in and out. What could happen is that if you change the epsilon prescription, you go from this situation to this situation, for instance. So which you have 0 in the far past and sigma out minus sigma in the far future. This, of course, doesn't change the memory effect. However, what changes is the value, for instance, in the far past. So as you can see from there, the value in the far past, or if you prefer to leading order in G when P out and P in are exactly the same, so the particles don't deflect, the result is 4G over R times, so let me neglect the TT projector for me, so it's there, of course. Plus of order G here. And this is what sometimes is called the Goldstone or the Coulombic field. So it's a time-independent contribution, which in particular fixes the shear of the system to be dictated by the Coulombic field or the static field of the massive particles in the far past. So let me call it the static contribution. And it's static because, as you can see, it no longer depends on you. All the dependence on you is in this dynamical bit here, which I didn't write down. Static piece. So yeah, tomorrow, before moving on beyond the soft limit, we will discuss a bit how, when using this approximation for the waveform, which is in a sense the simplest possible one, you can go back and rederive this result, and also how one can use it to calculate some contribution to the angular momentum, which depends on the static piece in particular. And the last comment I wanted to make is that, I mean, as I'm sure you know, again in the paper of the Stromengero Ziboyedo, they discussed how the static piece, in particular the TT part, can be dialed up and down by performing a super translation, right? So this is, in a sense, a way in which you are connecting to the other sets of lectures that you are attending to this week. So maybe I will start tomorrow by reviewing that and then move on to the soft spectra and the static contribution to the angular momentum. So, thanks. Any questions? Everybody's tired. Okay, I'm not sure exactly what the schedule requires of us right now, but I think there's a discussion session. Okay.